All right, so in this video, we're going to talk about solving logarithms. And I'm going to have 3 examples that kind of get a little increasing difficulty as time goes on. All right, so the idea behind solving logs, sorry about the bell. The idea behind solving logs is we have to get the log by itself first. So if you look at this example on the left, I have 2 log base 3 of x minus 3 equals 1. So before I can get this x out of a log, and remember solve means you need to tell me the value of x. So on all of these, when we finish, we're going to have x equals. So on this first one, I need to get log base 3 of x by itself. Well, currently, there's a negative 3 over there. So we need to move the 3 to the other side. Then I need to divide by 2. I'm trying to draw a G. So then we have log base 3 of x equals 2. And this is where we need to remember how to convert to exponential form. So when I say convert to exponential form, I'm trying to get rid of the log. And to get rid of the log, I make the original equation an exponent. This is called exponentiating both sides, which sounds fancy, but it's really not. So we need to make the original equation of log base 3 of x equals 2. Those need to become exponents. The beauty of algebra is I can pick any number to be the base of the exponent as long as I put the same number on both sides. So the base of my log is 3. So it's going to be very advantageous for us to choose an exponent base that's also 3. So in the parentheses that I drew, I'm going to choose an exponent base of 3. Here's why. When we go through, 3 log 3 cancels. And I'm just left with x equals 3 squared. Well, I know that 3 squared is 9. And we're done. So solving logs, we need to get the logarithm by itself. And then once the log is by itself, we can convert to exponential form and solve. Oops. I didn't mean to erase that, so hopefully you wrote that down. If you didn't, just rewind 2 seconds and go back. So the one on the right is actually, believe it or not, a very easy one. We have log base 5 of x plus 2 equals log base 5 of 12. So I have log base 5 over here. I have log base 5 over here. So if we have a log base on both sides of the equation, and the log has the same base, which it always will, I'm not going to put like log base 5 on the left side and log base 2 on the right side. So we have log 5 on both sides. Therefore, and this may be straightforward, maybe not. If you have a log base with something in parentheses equal to the same log base with something in parentheses, x plus 2 and 12 have to be the same number for this equation to work. So whatever's on the left side, the x plus 2 has to be the same as the 12. Because that's the way an equation works, is it's the exact same thing on left and right side. Therefore, the only way this equation is true is instead of the x, which just stands for an unknown value, so instead of that x has to be a 10, because 10 plus 2 is 12, and we'd get log base 5 of 12 on both sides. All right, so here's our worst case scenario, which I always like to show in a video. Just so you don't say my notes are always easier than class. So this is as bad as it can get. And it's really not that bad, so don't get too worried. So here I have two logs, and they're both on the same side. This creates a little bit of an issue because I can't convert to exponential form until I only have a single logarithm on one side. So here I'm somehow going to have to turn these two logs into one log. Well, lucky for us, last week and the week before, we talked about how to condense logarithms. So here, if I have multiple logs and I need one log, I need to condense. And condensing logs tells me that if I have two logs that are being added together, if I want to convert them to a singular log, I simply need to multiply the inputs together. So if two logs are being added, I need to take x and x minus 2, and I need to multiply those guys together. When I do that, I get an equation that looks like, that looks like this. And then just like my first example, I need to get x out of inside this log. It's trapped in the log, and we need to get it out. So I'm going to exponentiate both sides, and we're going to copy, again, the original equation has simply become exponents. And again, the base of the exponent we choose should match the base of the current log. So this question has a log base of 2. So the exponent base is also going to have a base of 2. Because 2 log 2 is going to go away, I'm going to be left with x squared minus 2x equals 8. And I'm sure we're getting super excited because anytime we see an x squared, and by now we've seen it a million times, so when we see an x squared, we know that one side of our equation needs to be 0, and one side of our equation needs to be 0, and we're probably going to have to factor to solve. So I need one side to be 0, so I'm going to move this 8 over. And then I need to factor. So factoring, we're looking for factors of negative 8 that add to negative 2, or combine to negative 2, I should say. So when we factor this, we're going to get x minus 4, x plus 2. Because negative 4 plus 2, negative 2. Negative 4 times 2 is negative 8. If you still need to go through the factor by grouping process, there's no shame in that. Just go through the factor by grouping and we'll all get to the same spot. So again, when I'm solving, I'm looking for x equals. But, so in the bottom, I have x minus 4 equals 0, therefore x equals 4. And in the second one, I have x plus 2 equals 0 in the second factor, so x must be negative 2. And here is our last bit of information. When you solve, now you probably want to be checking everything, but definitely check when you get two answers. So we discussed graphing logs earlier, and we discussed that the domain of a log cannot be negative. So the domain of a logarithm is 0 to infinity on the parent function, which just means we cannot plug in negative values into a log because it won't exist. It doesn't happen on the graph, so it won't happen when we do our algebraic solutions either. All that means is you need to plug in to check. So if we check x equals 4, I get log base 2 of 4 plus log base 2 of 4 minus 2. And then that gives me log base 2 of 4 plus log base 2 of 2. Now, this is 4 is positive, so we're fine. Here, 2 is positive, so we're fine. So, x equals 4 works. So we plug in x equals 4 to the original equation, and we're just double checking to make sure that it's not extraneous. So now we'll check x equals negative 2. So we have log base 2 of negative 2 plus log base 2 of negative 2 minus 2. Well, we have a big issue here. We can't have a negative inside the log. So as soon as I see the negative inside of the log, I need to be thinking that x equals negative 2 is not true because it's extraneous. Remember, extraneous, kind of in layman's terms, is a solution that we get algebraically. So the algebra tells us that negative 2 should work. However, from our knowledge of how logarithms work, it doesn't actually work. So we need to be checking our answers, but definitely when you factor and get 2 answers, just go back and double check probably the negative one. I'm not saying all negatives don't work, because sometimes our equation lets a negative work, so you need to plug it in and check, because the input of a log can never be negative after you do the math. So this right here, this log negative 2, is a big problem because I have a negative 2 input, and if you forget, if you put a log negative 2 in your calculator, it's going to shoot you back with a domain error because we can't have negative x values in the domain of a logarithm.